Hello, welcome back to Getting Started with Generative AI and Research. Today we'll be talking about data annotation and classification. So in 2007, a doctoral student at Oxford University, whose name was Kevin Shavinsky, was looking at images of galaxies like this one. But actually at that point of time, they were at much lower resolution. And generally galaxies come in various shapes and sizes, but most of them are either spiral, like our home galaxy, the Milky Way, or elliptical. And at the time, it was believed that all stars in elliptical galaxies were very old. And as stars age and reach around 10 billion years, they change in color and size, becoming red giants. And because elliptical galaxies contain many such stars, the images tend to be kind of reddish. And in contrast, spiral galaxies appear bluish as they contain many young, hot blue stars. So Shavinsky suspected that this conventional view actually incorrect, and that some elliptical galaxies might be not as old as previously thought, and could still be, having stars that are forming. And to test this hypothesis, he was classifying images from a publicly available dataset that was called Sloan Digital Sky Survey, and he manually reviewed around 50,000 images. And he was selecting which images contain elliptical galaxies and which spiral galaxies. And at the time, humans were better in this than computers, so he had to do it manually. So he then analyzes images, and it seems that his hypothesis might be true, but the effect was not strong enough, so he actually needed a much larger sample. But he didn't know how to do this because it would require much more work, and even to annotate these 50,000 images, he spent huge amount of time. So he was kind of sadly sitting in a pub, and then he met another researcher, Chris Lintott, and they come up with ideas. So let's maybe invite other people to help us to classify these images. Let's just invite volunteers. So he created this website that was called Galaxy Zoo. And they kind of managed to get an announcement of this project on BBC Radio, and they were actually flooded with volunteers. I think their site crashed, and then they fixed it, but the result was that there was much more annotations per hour done by volunteers that he was able to do on his own, and also this allowed them to annotate each image multiple times, and that actually ensures that this volunteer efforts were similar in quality to what a professional astronomer would do. And after that, it was discovered that, his hypothesis was actually true. So it's like to a new discovery and then to a set of new discoveries. So it was a very successful project. And what I wanted to say here is just that it seems that classifying or annotating images or text or some other data is something boring or not interesting, but it actually can play crucial science in research. And then they actually built on top of this project, and then they created another project that allow volunteers to annotate all sorts of data from all sorts of fields. And so I've just checked, and there is this project that is currently running on platform when people are annotating these shots from night camera, and they see if there are some animals, and if there are animals, what they're doing, and what types of animals are there. There are also projects when volunteers annotate images of cells, and all this project was very successful, and surprisingly, because some people would say that it's just citizen scientists, not like a professional scientist, they would probably get many things wrong, but this was successful, and it is useful in many fields. So we already have astronomy, biology, medicine. Also in social sciences, people need to annotate images, for example, images of protests, there's this data set that contain images from different events, and then you need to understand if it's a protest or not, if it's violent or not. And it was done by volunteers before or by scientists themselves, and then thanks to development of machine learning tools, and now everyone would call them AI tools, but a couple of years ago people were just saying machine learning tools. And it was also successful, and in many cases it turns out then once you have sufficient amount of annotated data, you can just train algorithms and they're performing much better. So people kind of moved to this machine learning annotated science. So this was state of the art before large language models appeared. And the problem with machine learning algorithms is that they require a lot of training data. So you need somehow to find the data that was already annotated, and sometimes it's just not available. And the second problem is that it requires a lot of technical expertise. So if you're just a social scientist with no background in computer science, it might be difficult for you to create your own machine learning algorithm. And this problem are now partly solved by large language models. And you probably know that large language models can be multimodal, which means that they accept as an input not only text but also images. And for example, there was a study that was showing that these images of protests, they can actually be very efficiently annotated by GPT vision model. So you ask it, if there's a protest or not, if it's violent or not, and it would give you a very accurate response. And the advantages of this is that they have competitive performance. They probably will be performing a bit less than specialized algorithms, but often good enough. But in some cases, you don't need any training data. For example, they inherently know what protest might look like, so you can just ask them about protests, and then you don't need to provide any training data. That wouldn't work for specialized field, right? They probably don't know what tumor is, so it's not universal strategy, but it's applicable in many cases. And it can be applied for all sorts of tasks. For example, I personally use it for when I needed to classify text if they're aligned to certain sustainable development goals. And there are existing approaches like machine learning standard approaches, but what me and my colleagues discovered is that actually large language models can perform out of the box and have a competitive, if not better performance, and you don't need any training data for that. So as I mentioned, there's many applications for this. I guess I will just give you one example, but you can imagine that there is much more examples like this. So in this paper, researchers were analyzing posts in like so-called manosphere, this kind of right-wing part of internet, and they tried to annotate posts and to see if they contain some violent speech. And there are actually good reasons to use large language models in this specific case, and that is because the people in these communities, they use a specific language, and it could contain kind of innocent words, but these words would actually refer to something violent, and the standard machine learning algorithms that would be trained on detecting like violent keywords would just miss this. So that's why researchers decided to try to use large language models. And another reason why you also want to maybe use automatic classification, not just humans, because the content may be highly disturbing, and it's actually, you have to care about your annotators too, and annotators, can be discomforted with this. So I was once annotating myself quite sensitive content, and I think that I'm not a sensitive person, but I was actually kind of not liking this experience. So that's another reason why you might prefer automatic classifiers. I didn't include examples of this post because I think they were kind of disturbing, but I've included the prompt that researchers have used. So you can pause the screen and to read it. It might be useful to know what like real prompts that real researchers are using to do research, and it could inspire you for your own prompts when you're doing similar tasks. So this table reflects the main results of the paper. So there are three numbers. The first one is agreement between models or between humans, and the second two numbers are different measures of accuracy. So you can see, for example, for the two humans, the agreement was 69%, and the accuracy was 85 and 87. And for example, for this model, the agreement with human B was 62. So it was lower than 69, but it was kind of pretty close. And accuracy was 84, then again, a bit lower than 85 or 87, but pretty close. So you can say that this particular model was actually performing like almost as human C, almost as well as two humans. And again, I want to remind you that this was actually a complicated task because there was all this kind of subtle language conventions, and these two humans was actually trained to learn about these conventions, and large language models probably also knew about this because it was trained on the whole internet. It was also trained on Reddit, so it's kind of knew about this, but it was not an easy test for it. So there's another aspect in this result. So you can see, for example, that there is this GPT-4/10, GPT-4/20, etc. It means that you can simultaneously send multiple examples to a model to analyze. For example, you can say, GPT, please analyze these 100 posts, please annotate them. And it could be that if you have too many of these posts, the performance would drop. And I think we actually see this, and the performance of GPT-4 when they sent 200 examples was not so good. but you also don't want to send it just one by one because it would require a lot of computational resources. And let's demonstrate you some practical nuances that you have when working with large language models. For example, that's one decision that you have to make when you're analyzing data. And also probably you don't want to make just arbitrary decision, but you want to test different settings and decide empirically what works best. So now I would like you to provide with some general advice if you're trying to use GPT for annotations. First of all, you should provide really detailed task description. It would be really important to ensure good results. Also, you have to provide few examples, and we already mentioned this a couple of times during the course because what's called few-shot learning actually works really well. So provide examples how you want your model to annotate or to classify some data from your examples. Then you also have to ensure that your measure is valid, and that's actually much more complicated than might seem from the first glance. I want to give you like one example. It comes from a classic machine learning, but I think it's like a very interesting example. So what was happening in this example is that people tried to use machine learning tools to automatically annotate these X-ray images. So they were trying to detect if there was some pathology in these images. So they trained an algorithm and it worked like really well. So it seems like, okay, we are doing well. We have accuracy score. This accuracy score is very high, 90 something. We solve the problem. But it is much more complicated because what people then did, they looked at what areas of image model actually kind of looks. So what you can do, you can see what weight to different parts of images the model give for its prediction. And so some of these are what you would expect. So you see, for example, that like in the center of the picture, the weights are higher. They kind of contribute to decision, which makes sense. What you can also notice is that weights here are quite high. And what's interesting is not only that they are high here, but that in this image, these weights are also high by absolute value, but they are kind of negative. So it seems that this part of image influence in one direction decision. For this case, and for this case, it's influenced strongly in another direction. And that's probably not what should happen because there is like nothing related to like chest here. But what you can notice that there is like some kind of text here. And this text is actually like some technical information, and this technical information would be different for different type of devices. So what model actually was doing, it was actually looking actively at type of devices to make its prediction. And why it might be useful, because there can be different types of settings where X-ray are taken. So one setting can be, like some routine screening when you wouldn't expect anyone to have something bad happening with them. It's just like routine screening, very low probability that you will detect something. And other settings is like in hospital when someone is already have a problem and then they're just checking and verifying. And in this case, the probability of having a pathology would be much, much higher. So, and then it means that just knowing the settings, you can guess pretty well if it will be positive or negative result, and that's what was happening. So you kind of have a measure that's perform really well, but it's not actually valid. It doesn't measure what you wanted to measure. So you have to always be very, very careful when you're trying to interpret the results of your high performance. You have to ensure that what you are measuring is exactly what you want the model to measure. And finally, what's also important if you are submitting paper to a good journal is just to ensure the robustness of your results. So just not do just one simple run. You have to see, what will happen if you change like your prompt a bit. If you change your prompt a bit and the results are suddenly completely different, then it's kind of suspicious. Maybe you have to recheck it. So you should probably try, a couple of models to see which one will perform best. Especially if you have a negative results when the model is not working, you cannot say that the model is not working if you just try, one model and try one prompt and try one settings. So that's an important part that you have to remember if you are going to submit your research in a good journal. So that's all for this part, and I will see you in next video.